Right. So in arithmetic and logic unit design, as we have seen in our first lectures, that the computers were uh, the 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 generations of your computers start from vacuum tube, then it is evaluated to by your transistors, the next generation, second generation computers. Third generation, they use the the integrated circuits. Then fourth generation, they use your very large scale integrated circuits, and current generation, they are using the ultra large scale integrated circuits. So the ALU, it performs the operations by using its hardware component, and that we call it as the processors they build from the transistors. So to build from the transistors means we talk about the basics of these transistors. We call logical gates. So these logical gates takes the computer arithmetic, which we discussed in terms of zeros and one. That means charged bit or uncharged bit, or charged electrical value or uncharged electrical value will be taken. Right. So as I said, the processors are built from your transistors. So how they are built? More accurately, the transistors constitute of your logical gates. The combination of transistors, gives the logical gates, and the logical gates constitute the functional units. From functional units, it constitutes the processors. So we can say that the processors are built from the transistors, right? So then see, in this case, the basic unit to perform the arithmetic and logic unit, we go with the transistors, then the logic gates, functional units, and finally it comes to your processor. So see, there are certain basic gates or basic logic gates. So you just recall what are the different operations that we performed in our previous lectures. We said the binary operations. Okay. In that binary operation, we have seen the binary addition. In the binary addition, we have seen the subtraction for single bit as well as your multi-bit, and binary your multiplication. And in one's complement and two's complement, in one's complement and your two's complement, we have seen that the whatever the binary value is there, that will be inverted. Each bits will be inverted in one's complement. In two's complement, the bits will be inverted, and finally another one is added, so we get the two's complement. Right? So these are few operations we perform. So to perform these operations, what are the basic gates which involve? Let us see. So first we find the first basic logic gate is AND gate. So this AND gate performs the simple computer arithmetic operation type, your multiplication. Right? So here this logic gate represents using this symbol. It takes two inputs and gives one output. Two input AND gate. Okay. So the Boolean expression for this logic gate, we write it as your Q is equal to A dot B, or it can also read as your A and B gives the result Q. Right? So how it performs? So let us see the single bit operations. Single bit multiplication operation. You just recall the single bit addition and single bit multiplication we have seen there in previous examples now. Okay. So multiplication, what it says, if the first operand is 0, second operand is 0, then when you multiplied 0 multiplied with 0 gives the result 0. So here A is 0, B is 0, and your result Q is 0. So this we call the truth values or truth value of this operation for this input. Similarly, if A is 1 and your B is 0, A is 1 and your B is 0, then multiplication of your 1 multiplied with 0, result is 0. So here you can see when A is 1, B is 0, the result is 0. If A is 0, if A is 0 and B is 1, then same 0 multiplied with 1 gives the result 0. Okay. So that is A is 0 and B is 1. And if both the inputs are 1, then 1 multiplied with 1, that gives the result 1. So A dot your B is equal to your Q result is 1. So from this truth table, it is very clear if you clearly observe the result with whatever the inputs are there, you can find that if both the inputs are 1, then only the result is 1. If any one input is non-1, then the result will be all zeros. So to remember the basic operation of this logic gate and you can see if both are 1, then the result is 1. If both the inputs are 1, then the result is 1. In all other cases, the result will be 0. Result will be 0. So this is the logic gate, and if you observe this, it gives the multiplication type operation, bitwise multiplication operations. They can be performed easily by the AND gate. Now comes to the next one. We have seen the binary addition, binary add operation. In binary add operation, we have seen the results with the single bit one. To do that, we have seen that 0 plus 0, 0 plus 1, 1 plus 0, or 1 plus 1. These are the basic single bit operations, binary additions that we perform. So to do that, there is a logic gate, we call that OR gate. The logic gate, we call it as OR gate. Okay. So this OR gate symbol, looks like the symbol, this one. So it is represented with this symbol. It takes two inputs, input A and input B, and it do the addition operation, and it gives the result. That is your Q. Right? So how it can be written? This logic gate, a Boolean expression of this logic gate with two inputs OR gate can be written as your result is equal to addition of your two numbers A plus B, two digits of your binary. Okay, so then it can be read as your A or B gives the result 1. So then here in truth table you can see now, 0. If you observe the values 0 plus 0, the simple binary operation which we have done, that is 0 plus 0 is 0. That means if A is 0, B is 0, then the result will be 0. If A is 1 and B is 0, the result is 1. If A is 1 and B is 0, the result is 1 here. Okay. So if both are 0, result is 0. If A is 1 and B is 0, result is 1. If B is 1 and A is 0, then your 0 plus 1, it gives the result 1. If both are 1, if A is 1 and B is 1, then it gives the result 1 plus 1 is equal to your 1, 0. And it gives the result your 1. Right? So this is the truth table of your logic gate or or from here you can see, from this truth table you can derive that if both the inputs are 0, then only the output is 0. If in all other cases the output is 1. If any one input is 1, then the output is 1. In previous case, if A and B, if both the inputs are 1 1, then the result is 1. In this case, if any one input is 1, then it is 1. If both the inputs are, we can say, if both the inputs are 0, then it is 0. In all other cases, it is 1. Okay, so this is the second basic unit or the logic gate which is used to build the ALU. Third one is the another basic logic gate which is used for building this arithmetic and logic unit is your exclusive OR or XOR gates. XOR gates are sometimes we represent with this symbol, this one, right? So the franchise, the gate representation symbol we use it is like your OR gate only, but along with that it is having the additional line here. It takes two inputs, input A and input B, and it gives the result Q. Okay, so here the Boolean expression which is right for this exclusive OR gate is Q is equal to A exclusive OR of your B, or it can be read as your A or B, but not both gives your Q. Not both gives Q. So it simply says that if both the inputs are, if A and B, if both the inputs are same, then the result is 0. If both are 0, it is 0. If both are 1, then it is 0. In all other cases, the result will be 1. The result will be 1. Okay. So here you can see if A is 0 and B is 0, if A is 0 and B is 0, then the result is 0. If A is 1, B is 0, then the result will be 1. If A is 0 and B is 1, result will be 1. If A is 1 and B is 1, result will be 0. So it simply says if both the inputs are same, then the result is 0. If both the inputs are same, the result is 0. In all other cases, the result is 1. Okay. So this gives your complement part. This is the inversion part. So now comes to the another gate for ones complement which we use there. In ones complement, it said if we have the bit stream like 1 1 1 0 0 0, then the ones complement said that all the bits will be inverted to represent the ones complement. That is, 1 becomes 0, 0 becomes 1, 0 becomes 1, 1 becomes 0, 0 0 0 1 1 1. So this operation can be performed with a logic gate we call the NOT gate. So NOT gate, it simply inverts, or we call it as inverter or your NOT gate. The Boolean expression for this one is Q is equal to not A, or we say the complement of your A, or it reads as your inverse of A gives Q. So here you can see 0 become 1, 1 become your 0, 0 become 1, and 1 become 0. So these are the basic logic gates which we use to build the arithmetic logic unit. Why only these are taken? Why not other gates are taken? That means in ALU, whatever the examples we have seen there, we have performed the addition operation. For addition operation, the OR gate will be used. For multiplication operation, your AND gate will be used. For inverse purpose or for performing any subtraction operation, okay, you may use the inverse operation like ones complement or twos complement. So you need the OR gate as well as the NOT gates. Okay, so few gates are enough to build the logical gate. I mean the ALU. So we are not considering the your NAND gate or your NOR gate. Okay, so we are just considering only the basic gates. Your AND gate. In AND gate, remember, when both inputs are 0, then only, when both the inputs are 1, then only the result will be 1. In all other cases, it is 0. Okay. In OR gate, if both the inputs are 0, then only it is 0. In all other cases, it's 1. In exclusive OR gate, if both the inputs are same in status, then the result is 0. In all other cases, the result is 1. In NOT gate, it is simply inverting the values. It is simply inverting the values. So now, let us see the logic gates which used to build an ALU. So in our previous examples where we talked about the IEEE 754 floating point representation, in floating point representation, we followed two methods. One is your single precision and your double precision. So what we said, single precision uses 32 bits representation. Double precision means your 64 bits representation of your floating point. 32 bits representation of your floating point, right? So now, to perform the operations on this single precision floating point operation, addition or subtraction, multiplication, or 64 bits. So in our case, we are going to take the 32 bit for our discussion, 32 bit ALU. So we need to build an ALU to perform the 32 bits. 32 bits. Is my voice is clear? Is my voice is clear? Okay, thank you. Yeah. So we use this 32 bits. If you recall our computer, architecture, Van Neumann machine, or your, the architecture, there we found that, in that we found CPU is there. In that CPU, we find the control unit, and we find the functional unit also. And then we found the registers there. So here we talk about this control unit and the functional unit. Functional unit is your ALU. Control unit is how what kind of operation it should be performed. So the ALU the looks like this. It takes 32 bits input, 32 bits of input, like we just performed the every gate takes two inputs except your NOT gate, right? A and B. So 32 bits input and it produces the result 32 bits. So here this ALU will takes a two 32-bit values A and B, okay, and two control lines, two bits for your control line. 2 bits means how much? You can see 2 bits means the representation of your 2 bits. You can write 0, 0, 0, 1, 1, 0, 1, 1. So control line having 2 bits means at most how many operations it covers? It covers 4 operations. That means, for example, 4 operations. For example, it may cover 0, 0 means this control signal may give for your addition. 0, 1 means it gives another operation like your subtraction. 1, 0 means it may give your bitwise and operation. And 1, 1 means it may give you a bitwise or operations. So that it says, depending on the value of control lines, the output will be, the output of your ALU will be, it may be your adding, add values, addition operation value or subtraction operation value, or your bitwise AND operation value, or your bitwise your OR operation result. So note here, this is an interface. This is an interface, which one your control unit and your ALU. This is an interface for the ALU. This part is an interface for your ALU. It says what goes in and what comes out. What goes into your ALU and what comes out of your ALU. So here you can see this is the abstraction. So here we are not talking about how it works. We'll discuss this, how it works one by one. But from this, you can find that you will get two inputs. You can give two inputs to this ALU, and these two inputs will be given as your operand 1 and your operand 2 will be given to a control signal. It may be your addition operation. So this will be controlled by your control signals. So that finds from your arithmetic set, whether addition operation or subtraction operation or multiplication or other operations. So it gives once the operation is performed, it gives a result. It gives a result. So this result, can be anything. So also note here that there are three status outputs always. So you can find 0, carry and overflow. 0, carry and overflow. The result can be 0. The result can be 0. Or if the result is not 0, then you can find carry. Was there a carry, or did the operation results in a overflow? So these, the borrow and carry we have observed in our previous example, right? So simply you can see what is carry means. Suppose we have given two numbers. Suppose 1 1 1 1 0 1, and do the addition of this. Your 1 0 1 1 1. So to do this, bitwise operations. To do this bitwise operations, I mean the addition. So then we have seen this example that 1 plus 1 is 1 0. So 0 is here and 1 goes in the carry. Correct? So here that carry will be given as an input again. So 1 plus 0 is 1 and 1 plus 1 is 1 0. So 0 will be here and 1 here. Okay. So as a result, we have seen for this number as a result 1 1 1 1 0 1 and 1 0 1 1 1. We have find the result that the 1 0 1 0 1 0 0. So here you can see the carry bit. We have seen everywhere the carry bit is there. Okay. And when we did the subtraction operation, we followed the borrows. Okay. In borrows means we found the doing this borrow from here, 1 minus 1 is 0, but 0 minus 1 not possible. So we borrow this from its neighbor so that the overflow comes into the picture. So here it says that the carry means it's set to 1 if there is a carry in the most significant bit, which could not output in a given 32 bit in this result. Okay, so that will go and store in a carry. Overflow is set to 1 of the same operand or of the operand have the same sign. Okay, and the result has a different sign. That means if you are adding 2 plus a plus b positive values, but if the result comes like minus value of this, addition of this comes like minus c, then it gives a different sign, right? So for example, as we said, if sum of two positive numbers yields a negative result, then you will find the overflow occurs. Now let us see what is there inside this CLU, how it will build by using your gates. So let us see a 32 bitwise or logic gates. 32 bitwise arithmetic and logic gate. So here what we say, there will be 32 A inputs will be there, 32 B inputs will be there, because we are taking a single precision floating point IEEE 744 representation. So it takes 32 bits input. So to do the bitwise operation, every gate takes two inputs, A and B. Okay. So in this, we are trying to discuss this ALU arithmetic and logic unit with 32 bitwise OR. So we use the OR gates. How many OR gates? We are doing the 32-bit floating point representation, right? In floating point representation, for every bit you need one gate. So we call this your 32 bitwise the OR gate. So in this interface, what we said, it takes your 32 A bits and 32 B bits. It's an ALU. Result will come. Then you may find your zero, carry, and your overflow, right? Overflow, right? So and then you are giving the 2 bits control signal, okay, to select this. So to build this one, it requires 32 OR gates. So this is the first zero. They are numbered with all these 32 OR gates are numbered with 0, 1, 2, 3 up to 31. Limit. So the first gate is 0 gate. So this gate takes the 32 bits A representation, operand 1 0th bit and operand 2 0th bit, and it gives a result, 0th bit results. Second one is second operand first bit, it gives result 1. Similarly, for the 30th bit of your first operand and 30th bit of your second operand, 31st bit of your, so it is a bitwise operation. So you just recall, our example. If you just recall our example, that is your 1 1 1 1 0 1, your 1 0 1 1 1. So if you give the bit positions, 0 bit position, 1 2 3 4 and 5 bit positions, then this 0 will be given to this inputs. Like A is 1, this is first operand 1 suppose, and this is operand 2, then 1 and B is also 1, the 0th bits will be given 1 and 1, the result will be 1 0. So here carry is there, that carry goes and inputs. So here we are giving the carry here, right? So now again these bit positions are given. So the next bit position, 1 bit positions will be given here, 2 bit positions will be given here, 3 bit positions will be given here, and so it continues up to 30th bit position given here, 31st bit positions will given here, and this builds the 32 bitwise operation. So building the logic gate to your 32 bit OR on 2 inputs is easy, as said, as each bit is independent and we just need 32 OR gates in parallel. So this control, just recall this one, this ALU which is controlling takes 32A bits, 32B bits, and it gives the result. Suppose if you want to build the ALU 32 bitwise, not or suppose the and in that case, all these gates, these gates will be replaced with the AND gates. So it takes A 32 bits, and your B 32 bits, and it gives the result 32 bit and 32 bit and. So in this complete control is having 32 AND gates. So every OR gate will be replaced with the AND gate. This. So whatever output comes, that output will given to. So these outputs comes as your 32-bit AND gate. So now let's see the simple example for ALU unit for 1-bit adder. ALU unit for 1-bit adder. 1-bit adder means bitwise adder. We are just adding, taking two inputs, and it produce one output. Okay. So to sum up two values, we have to repeatedly add two bits, and this may produce a carry. So to perform the addition operation, so the ALU unit use the 1-bit adder. What is this 1-bit adder? The 1-bit adder takes two inputs, and gives the result. Okay, but when we perform the previous, the example, if you consider previous example, what we found 1 1 1 1 0 1, you take 1 0 1 1 1. Then when we performing 1-bit adder, so 1 plus 1 we add, it is 2. So 2 represent as your 1 0. So 0 is here and 1 is here. We set this as your carry. Right? In this carry, when we are going to doing this operation here for the second bit position operation, then what we are doing, whatever the result is came here, that is 1 0. So this we call the carry. This is also carry. So we called it as your carry out. So this carry out is given as your carry in. Okay, carry in. Right? So the carry out comes, so that will be given to carry in. So along with the inputs, we also have some other input we call carry in. So you will get, along with A and B input in 1-bit adder, you will also have sometimes the carry in. So total it becomes three inputs, and it gives the result. So when you are adding this inputs, you will, in the result, sometimes you are finding carry out. So that carry out is given as an input in terms of your carry in. So this is the basic representation of your 1-bit adder. There will be two inputs. When two inputs are added, it may get some carry outs. So that carry outs converted into your carry in, then it becomes three inputs, and from that three inputs you will get the result. So in this truth table of your 1-bit adder, you can see there will be two inputs and one result. Okay. In that result, if it finds any carry out, that carry out is converted into your carry in. So total that becomes three inputs, and it gives the result. This process continues for 32-bit floating point adder. So what it says, to sum up two values, we have to repeatedly add two bits, and this may produce a carry, as we saw just in this example. So the columns further up need to accept the carry as input. That is what we observed here. 1 1 1 1 0 1 1 0 1 1 1. As we said, when we are adding, then you will get some carry out. That carry out will be accepted as your carry in. So that is what. So columns further, these columns further up need to accept a carry as input along with two inputs and produce a 1-bit output and another carry for the next column up. So the component which will perform a 1-bit add, that receiving a carry in and producing a 1-bit output and a carry out is called a full adder. Full adder. So here you can see if input A and B are 0, then 0 plus 0 result is 0. So you don't have any carry here and you don't have any carry in, carry out. In the second case, you can see 0 and 1. So 0 plus 1 is equal to 1. The result is 1. So here also you don't have any carry in and carry out. So in the third case, if you see here, A is 1, B is 0, result is 1. Result is 1. Okay. When in the fourth case, when A is 1, B is 1, 1 plus 1 is your 1, 0. So this 0 is your result, 1 is your carry out. 1 is your carry out. Okay. See, when both are again, when this is carry out, then this carry out will be given as an input, carry in for the next one. When it gives carry in to the next one, then it becomes your 0, 0, 1 plus 0 plus 0. So that gives the result 1, carry out is 0. Right? When carry in is 1 and if the combination is A is 0 and B is 1, result is 0 because here 1 plus 1 is 1, 0, result is 0, 1 is carry out. If carry in is 1 and your input A is 1 and B is 0, then you can see 1 plus 1 is 2, 2 plus 0 is 2. So 2 is written as your 1, 0. 0 will be the result here. 1 is carried out. Similarly, when carry is in and if both the inputs are suppose 1 and 1, it becomes 1 plus 1 is 2, 2 plus 1 is 3, 3 will be written as 1, 1. So result is 1 as well as carry out will be there, right? So here, overall, what we are saying, we will have 2 bits input as well as carry. So total 3 bits, So 2 to the power of 3 is equal to 8 possibilities. 8 possibilities. So those 8 possibilities can be written as in this symbol. 1, 2, 3, 4, 5, 6, 7, 8 possibilities will be there for 1-bit adder. Okay. Okay. Then comes to the ALU 1-bit adder with the example you can see here. Internally, here is what a full adder looks like with the just 5 logic gates. Okay, this 1-bit adder internally built with 5 logic gates. So this total is your ALU 32-bit. To perform 1-bit adder, one logic gate, the 5 logic gates are used. What are those? The exclusive OR gate, your AND gate, and your OR gates. But okay, so how many total gates in this to perform this the full adder operation? It requires 5 gates: 1, 2, 3, 4, and 5 logic gates. Okay, so what it covers in full adder, just recall this. There will be 2 inputs, right? In full adder, 2 inputs. One, this is A, this is B. This one is carry in. You are having the carry out, and finally you are having the result, right? So Inside this, you find for inputs you are using two gates. One is exclusive OR gate, another one is AND gate. For carry in, you are using another input which is given to your exclusive OR, and for carry out one gate is used, and finally you will get the result. So let us see here, to make a 32-bit full adder, we simply have to string 32 of these 1-bit full adder. If it is only 1 bit, means we are having only one adder here. 32 bits full adder means like this, there are 32, the logic gates will be there, means adders will be there. So 32 parallel gates we use, multiplied with your 5, it gives the complete 32-bit full adder. ALU unit with 32-bit full adder, 32-bit full adder. Okay. So except for the least significant adder, each one is going to receive its carry from the one below and pass up its own carry to the one above. So let us see here in this example, for all these 8 combination of your operations with 3 inputs, carry in, input 1 and input 2 are operand 1, operand 2 inputs. Okay. So see, sorry. Okay. Input A is 0. Here is 0. And A is 0. B is 0. A is 0. B is 0. Okay. So then let us find what is the result and what is the output. Whether the hardware design of your ALU works correctly or not. Just check it out with these 5 gates. Now, as we know, when you give 0 and 0 as an input to your exclusive OR gate, what it says, if both the inputs are same, the result is 0. The result is 0, right? Then the same 0, 0 inputs are given to your AND gate. What AND gate says, if both the inputs, when it is multiplied, if both the inputs are 1, then only it 1. In all other cases, it is 0. So 0 multiplied with 0, result is 0 here. Okay. Now see, now carry is 0 for the first one, right? There are no carries for the first bit position, suppose. Then this 0 is given as an input to exclusive OR, and this 0 is also given, then we know that the result will be your 0. The result will be 0. So here, this output 0 is given to AND gate, this output 0 is given to AND gate. I mean, the carry in is also given to an input to your AND gate. Then 0 multiplied with 0, the result is 0. So now, the input to your exclusive OR, to get whether is there any carry or not, you can see 0 plus 0, result is 0. So here you can see carry out is 0, your result is also 0. Result is also 0. So for the most significant bit, if the carry is 1, then we ran out of the bits to store the result, right? For that, how it is, in the second case, you can see carry is 0, input A is 0, input B is 1. Then let us see what is the result and what is the carry out. So here you can see 0 and 1. So the inputs are different. When the inputs are different, the exclusive OR output is 1. Okay. And when this 0 and 1 supplied to your AND gate, 0, 1. Okay. 0 multiplied with 1, result is 0. Now comes here, the Cin is 0 and your 1 is given as an input to your exclusive OR gate, then it gives the result 1. So same, the output of your exclusive OR given as an input to your AND gate, and your Cin is given as an input, then 0 into 0 is 0. The OR gate result for 0 plus 0, result is 0. Result is 0. Okay. So then another number, if you take the third case, C in for this, let us see whether this hardware is working correctly or not. C in is 0 and your input A and B is A is 1, B is 0. So then here one exclusive or 0, it gives the result is 1. So result is 1. Okay. Now again 1 and carry is 0 for this. So one exclusive OR of your 0, the result is 1. And then for carry out, is there any carry out checking means your 0, here is 0, here is 1. 0 multiplied with 1, result is 0. So we'll get the 0. So from here the input is 1, from here the input is 0. So 1 multiplied with 0 as per your AND gate, result is 0. So here 0 plus 0, result is 0. So what is there? Your result is 1 here and carry out is 0. Result is 1 and carry out is 0. Okay. Similarly, if you see the case where the C in is 1, where the C in is 1, where the C in is 1. So, how it is coming. Again, you just recall our example 1, 1, 1, 1, 0, 1, and your 1, 0, 1, 1, 1. So in this case, you just see inputs 1 and 1. When it is given, then what is the result? Result we are finding 0 and there is carry 1, right? 1, 0 means carry become 1. So that's the case here to do this operation. So in this operation, you can see now A is 0 for this column, Okay. For this column, A is 0, B is 1, and your carry in is 1. And see what is the result here then. 1 plus your 0, the exclusive OR operation which is performed by this, result will be 1. Okay. So then that is given as an input. So here it becomes 1 exclusive 1. When both the inputs are same, result will be 0. Result will be same, right? Both zeros, result is 0. Both are 1, result is 1. So now here you can see A is 1 and your B is A is 0, B is 1 from this case in this column. Okay, we are just finding the value for this. So 0 multiplied with 1, it is 0. From here, 1 input and 1 input, you can see 1 multiplied with your 1, result is 1. So then your OR operation is 0 plus 1 is equal to 1. So your carry out is 1. Your result is 0. So what you say, 1 plus 0 plus 1 is 2. So 0 will be here and carry out will be given as an input. Carry out will be given as an input, carry in. So this carry out, so here you can see carry out is 1. So carry out is 1 here as a 1, 0. Right? So now comes to the next one. Here now we have 3 ones, right? 3 ones. 1, 1, 1. So 1, 1, 1 means it is the case of the third operation. Carry in is 1. Your input is first operand is 1, second operand is 1 in this example. 1, 1, 1. It becomes 3. So let us see when it is 1 and both the inputs are also 1. In our example case, 1, 1, 1, 0, 1. And 1, 0, 1, 1, 1. So here we got the 0 carries 1. Here is 0 carries 1. In this case, if 3 ones are there, so 1 exclusive OR of 1, result is 0. So output of this one is 0. Then here the 0 and 1 is there. So 1 exclusive OR of 0, result is 1, because both the inputs are different. Result is 1. So here when you give this input 0 and 1 here, here is 1 and 1. 1 and 1 result is 1. 0 and 1 result is 0. When you add 1 plus 0, result is your 1. So carry out is 1. Carry out is 1. When 3 bits become 0, 1, 1, 1, 1, 1, 1. So result is 0. Sorry, 1. Your result is 1, and 1 will be in your carry out and carry in. Okay. Then comes to the next case, 1 plus 1. Here 1, 1, 0. That means carry in is 1, input 1 is 1, input 2 is 0. In that case, you can see carry is 1, input 1 is 1, and your another second input is 0. In that case, if you find 1 exclusive OR of your 0, that is equal to your 1. So output is 1. When both are same, result is 0. 1 exclusive OR of 1 is 0. So now here you can see 0 input and 1 input. So result is 0 here. If both are 1, result is 1. Then you add 0 plus 1. It gives carry out is 1. Okay. So here you can see carry, the C in is 1 and A is 1 and your B is 0 in our case, then your result is 0 and your carry out is 1. Carry out is 1. Okay. So is it clear? Are you able to follow me? Are you able to follow me? Is it clear? Good, good. Yeah, thank you. Thank you. Yeah. So this is the we call this as your ALU unit with 1 bit adder. But similarly, if we have 32 bits as we represented in IEEE format, we find the 32 bits, right? In 32 bit, what we use? First bit is your sine bit. Then 8 bits are your exponential bits, and the remaining 23 bits your fractional bits, right? Fractional part. So total 32 bits. So for this total 32 bits. So for this total 32 bits, how many units we need? 32 1 bit full adders are required. 32 1 bit full adders are required for ALU. Okay, we just followed for only one full bit adder. This one full bit adder. So like this, for 32 bits, 32 units are required. 32 units are required. Okay. So in every 32 units, how many gates will be used? Means 5 gates will be used. 5 gates will be used. Okay. So this is another example, some simple example of adding 0, 0 and 1, and this is what we just observed in the previous slide also. So similarly, as said, ALU unit with 32-bit adder means it takes 32 A inputs, 32 A inputs and 32 B inputs. Okay, 32 A inputs and 32 bit B inputs. So in this one, inside this adder, you will find there will be 0, 1 up to 31 1 bit full adders are there. In this 1 bit full adders, how many gates? 5 gates will be there. 5 gates will be there. Okay. So all these 32 bits are together become one circuit, or we call the processor control, which is having 32 input bits and your one carry in. And for when adding this carry in input A and input B, it gives some result. In that result, it may have the carry out. So this carry out will be again given as an input to this every adder. That means what? Here you can see for the first bit adder, the first 0 bits are given. When 0 bits are given, here the C in will be 0. When this A and B are added, in the result, if it is a non-zero, suppose if it is a non-zero, you will get the carry out. That carry out will be that out will be converted as an input to the next adder. So from every 1-bit adder, carry out is given as an input to the next 1-bit adder. This continues until the most significant 1-bit adder adds the result and gives the total result as your 32-bit result. So with this, the most functional units can be built from the logical gates. What are those functional units? It may be your subtractor, operation, logical gate. We just have seen the addition now for multiplication and your multiplier and your multiplexer. So some functional units can be very complex, such as your branch predictors. So we are going to talk about these branch predictors in our data part. Okay. So for every functional unit, or most of the functional units built from the logical gates. What are those basic logical gates we use? Your AND gate, your OR gate, your exclusive OR gate, and your NOT gate. So by using these basic logical gates, one can build the arithmetic and logic unit for 1-bit adder, for the 1-bit adder, or subtractor, or the multiplier and multiplexer, or 32-bit adder, or subtractor, or multiplier and multiplexer, or your 64-bit. If it is a double precision, then 64 bits adders, subtractors, multiplier, and your multiplexers. So with this, we can say that how we can build the ALUs